Hi guys, I want to give you a little basic overview of chapter 2, some of the main highlights. Hopefully this helps you as you are studying for your test. But I wanted to give you pretty much a little bit about enzymes, a little bit about water, everything we went over during the chapter, kind of in a summary. So here's a water molecule here, and here this is called methane. It's a carbon in the middle with 4 hydrogens on the outside, where this one, we have for water, we have our oxygen. That's our main element, and then our 2 hydrogens on the side. So I'm going to start off talking about what was different about these 2 molecules with respect to their electrons. So here's our electrons for our water molecule. They are in blue, and then for hydrogen they are red. These electrons here and here are being shared between these 2. All right, we call that a covalent bond. Now if we look over here with our methane, they're also being shared, but in more places. All this is saying, guys, is we have 2 covalent bonds here, and we have 4 covalent bonds here. So let's talk about the difference between these bonds. These bonds here are called polar covalent bonds. Okay. Now our ones over here, a little bit different. These are called nonpolar covalent bonds. Okay. So let's talk about what is actually happening to make these bonds different between them. If we're talking about the polar covalent bonds, I'm going to use one of the red electrons here for hydrogen. So what's going on is as they're being shared, this electron is going around hydrogen, but then it's going around oxygen. It just keeps going around and around and around and around and around and around. So essentially oxygen has it most of the time. Every now and again, it's going to go back to hydrogen, but for its most part, it's going to be around our oxygen, okay? Now, if you guys recall, our electrons are negatively charged, and since that electron is around oxygen most of the time, we say that the oxygen in water is slightly negative, okay? And since the electron, again, is around oxygen more often, that means the hydrogen doesn't have it as often, so the hydrogens are going to be slightly positive, okay? That's a Greek symbol for delta. It means partially. So in conclusion, guys, water, we call it a polar molecule because the oxygen and the hydrogen are charged. The oxygen is slightly negative, the hydrogens are slightly positive, okay? If we look over here with methane, it says it's nonpolar. Here's what the difference is. I'm going to use the hydrogen electron once again. It's going to go around hydrogen once, and then it's going to go around carbon. And then it's going to go back, okay? It just keeps going back and forth. It's like a figure 8. It's not unevenly shared like the polar covalent bond. So the polar covalent bond, this shares electrons unevenly. The nonpolar covalent bond shares it evenly. So with all of these atoms, even the carbon in the middle, there's no charge. It's not positive, it's not negative, it's neutral. Whereas our oxygen is negatively charged and our hydrogen is positively charged. So, moral of the story, guys, polar covalent bonds will result in an atom, a molecule that has charges on each of the atoms. But nonpolar covalent bonds, nothing's going to be charged, okay? So how can we apply this to our world? Let me show you here. So let's say I get a beaker, and I'm going to put some water in it. Okay? So here's our beaker. Here's our little spout for it. And I'm going to put some water in. I will use a blue color for it. I know there's going to be a meniscus, but I'm going to make it subtle. So all this is water. Okay? Now let's say that I'm going to add some oil to it. All right? I don't have a yellow color, guys, so I'm just going to use orange for oil. So I'm going to pour some oil in it, and then the oil forms right on top. It might mix at first, but then they separate. So this is going to be our oil, and then down at the bottom is going to be our water. Now, why do they separate? Well, they separate because water is polar meaning the electrons are not shared evenly, and oil is nonpolar, and that never changes. Oil is always polar, water is always nonpolar. Oil, the electrons are always shared equally. Water, it's shared unequally. So that is literally why these two things separate. Now, why does the oil go to the top? That deals with density. The oil is less dense than the water. So if it was opposite, the water would be on top, but in this case, that's how it goes, all right? Our properties of water we talked about, guys: cohesion, adhesion, capillary action. Just to give you a quick run view of those: cohesion, if you think you cooperate with someone, it has a prefix CO on it. If you cooperate, you work together with them. Cohesion is literally water working together with water. So if we want to talk about cohesion, it is like whenever water is sticking together. With water sticking together, guys, that's like if you have a water bottle, okay, that's why all the water is together and there's not spaces in between, all right? All of that is cohesion. So with cohesion, let me draw a few water molecules up here. I'm not going to draw too many. There's our hydrogens in each water molecule. Here's our oxygens. Okay, so we're going to have two different bonds going over here. Now this is going to create cohesion. This is what cohesion would look like if we were able to see the bonds. Now, holding one water molecule together right here and right here, these are your polar covalent bonds. So if we're talking about one water molecule, they're held together by polar covalent bonds. Now, if we're talking about different bonds that hold adjacent water molecules together, these are going to be different. These are not going to be polar covalent bonds. They're going to be much weaker than polar covalent bonds. So given that the oxygen, we said it's slightly negative, the hydrogen is slightly positive, I'm going to make a bond between the oxygen of one molecule and the hydrogen of another. Same thing here, same thing here, and same thing here. Now these bonds here are called our hydrogen bonds. Okay? These are much weaker, as I said earlier. So polar covalent bonds are really strong. You're never going to separate those. The hydrogen bonds, very weak. If you stick your finger in water, you are breaking the hydrogen bonds. If you jump in water, like jump in a pool, you do a cannonball, you just broke a ton of hydrogen bonds. Now, some of them are going to reform, and some of them are actually going to be attached to your skin. That's why you get wet. All right. So if you were to jump in a pool and you get water on you, all that water splashes everywhere, the water clings to you. So the water is actually making hydrogen bonds with your skin as well. Now those bonds are through adhesion. So water sticking to water, this is cohesion, okay? But then when water sticks to, I don't know, let's say, I got a different color here. That's my best shirt I got there. When water sticks to your shirt or your skin or whatever, those hydrogen bonds formed with that, they're still bonds, okay? But that's adhesion. So water sticking to water is cohesion, water sticking to other things, that's adhesion, okay? If we talk about going on from this, if we talk about plants and trees and things like that, okay? I'm going to give you my best representation of a tree here. So here's our ground. There's our trunk. Oh yeah, there you go. That's lovely. There's our tree, okay? You guys know, through previous years, that we need water up in the leaves of the tree. But when it rains, the water goes into the ground. Okay, so we got our roots here. What's going to happen here, guys, is the water has to enter through the roots, and it has to climb upward to get all the way up in this area here. So that's where our water has to go. So if we're looking there, the water's going against gravity. It's going upward, okay? How does it happen? I know if I have a ball in my hand, I drop it, that ball's going down. Gravity takes it down. Here's what happens, guys. If I have a small tube, I'm going to take a little tube out of the tree. or enlarge it, okay? We're gonna have water molecules all through these little tubes. They're like your veins and arteries, but for trees. The water is actually going to cling to the sides of these tubes for the trees. And what's gonna happen is the water is going to actually use other water molecules. So let me get a different color here. This will be our special water molecule. So what he's going to do is he's going to essentially use these other water molecules as a ladder, and he's just going to keep climbing upward, 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 and then place himself right here, okay? Now if we have another one, we'll say he's down here, okay? Again, guys, these are all water molecules. This one is going to keep climbing upward, 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 and then he's going to go actually on top of the green one, okay? So the water climbing up this narrow tube is able to attach to the side. So it attaching to the side of the tube in trees, that's adhesion. And then the water using other water as a ladder, essentially, that's cohesion. This whole process is called capillary action. Okay? All right. So we talked about cohesion. Cohesion was with the hydrogen bonds, water to water. It's our reason for having surface tension on the top of water. That's why some animals can, run across the water. We had our adhesion, which is water clinging to other things, okay? And now we have capillary action. So just so you guys know about water, we talked about water and we talked about oil. Water was polar, oil was non-polar, okay? They separated, so there's not going to be any adhesion between the water and the oil. Okay, so polar molecules, like water, can join and mix with other polar molecules. But polar molecules cannot mix with non-polar molecules. All right? So just so you guys know, polar and polar combine, non-polar and polar separate, and then non-polar and non-polar, those are two lights, they would combine as well. Okay? The last property of water we have to go over is the high specific heat of water. I'm not going to draw anything on that. I'm just going to talk about it real quick. When we say water has a high specific heat, what that means is it takes a whole heck of a lot of energy for water to raise its temperature by 1 degree, okay? Why is that good for us? Well, we're made of 72% water, somewhere around there. If we have 72% water in our bodies and it's 32 degrees outside and water changes very quickly, if you go outside, your internal body is going to change to 32 degrees. That's not good, right? Because your internal water would actually be freezing and you would die. So water having a high specific heat is really good, okay? The last thing we went over, guys, was enzymes, okay? I'm just going to do the same example I had in class. Here's our enzyme. Enzymes are a type of protein, okay? On the enzyme, we have our active site right here. All right. So, parts of an enzyme. We have the enzyme, we have the active site, the enzyme's a protein, those are our parts. Now, attaching to our enzyme, this is going to be our substrate. It's a fancy word for a reactant, okay? The substrate is not part of the enzyme, but it's going to bind to the enzyme. So, what's going to happen here, guys, is we're going to have our enzyme with our active site. The substrate is going to bond to the active site on the enzyme. So it'll look something like this, it bonded, okay? And then the goal of these enzymes is to lower the amount of energy we need to break something down. So we're going to have some type of reaction occur, and in the end, after the enzyme is done doing its job, we're not going to have that nice big substrate anymore. Instead, we're going to have our products, okay? So here will be one product, and here will be another product, okay? So the goal of these enzymes, guys, is to lower the amount of energy we need for a reaction to occur and to convert the substrate or the reactants into products, okay? Like I said, guys, enzymes do this by lowering our amount of activation energy. So let me just show you a graph of that real quick that we went over in class, and then we'll be good with this. So here was our graph. We had energy on this side, and we had time of reaction on this side. As I go more to the right, time is going to increase, obviously. So we started here. We're going to go all the way up and all the way down. All right. Our reactants are going to be here, and our products are going to be formed all the way down here. Okay. Our activation energy is the amount of energy we need for this reaction to occur. So our activation energy, guys, is the size of the hill. So if I draw a line going across from reactants, this right here, that is our activation energy. Okay? It does not go all the way down to 0 on our energy. It just goes with the size of the hill. That's our reactants, okay? Now, let's say this is a reaction where an enzyme is not present. It's going to take a whole heck of a lot of energy for you to get up that hill. So what the reaction looks like on a graph with an enzyme is it's still going to start at the same energy. It's going to go across, it's going to go up, but the hill is not going to be that steep or that high. And then it's going to once again go with where the reactants are. So this one here is where the enzyme is present. Okay, and then obviously the, I guess you can call it the plum colored one or the berry colored one, the enzyme is absent here, okay? You guys can see that the hill is much, bigger when the enzyme is absent. This is why when you're sick, your enzymes become denatured, they're not working as well, and the hill that you have to go over is much bigger, because when the enzyme becomes denatured, guys, if I draw a picture of our enzyme we had, okay, once it becomes denatured, it loses its shape. It loses that active site. So the substrate can no longer bond because the active site is gone. All right? So the active site is gone there. And that's why when you're sick, the enzyme doesn't work, so you always have to use that bigger hill, meaning you're going to expel more energy. All right? A lot of information, guys, I went over with you in the last few minutes, in the last few weeks of class. So make sure you study. Hopefully this video helped, and have a good rest of your day, guys.